So we left off the last video talking about corner points, and I'm listing them now. So here's the obvious one here. This corner is 0, 0. This corner of the colored shaded area is 15, 0. This one I mean, because especially since we had already worked this problem another way, you can see the intersection right there is your 5 and 10 is what it came out to be. But if you're not sure what it is and you don't have it nicely labeled, you can always use a substitution method or additional elimination to come up with your numbers. So x is 5, and if I plugged it in and found out that y was 10, so I get the 5, 10 ordered pair that goes right here. And then the last one's here was the one that we're saying was a fraction, so it's 0 and then 13 and 1/3. So those are our corner points, and we're going to learn in our next set that the solution to our linear programming is going to occur at one of the corner points, and you know already that it occurred at 5, 10. Well, I'll show you how it happens without guessing. So the key concept is if there is a maximum or minimum value of a linear objective function, it will occur at one or more of the corner points of the feasible region. So to solve, here's our steps. To solve a linear programming problem, you have to write the inequalities that match the problem. You have to write the objective function. Then once you do that, you're going to graph the inequalities and shade to find the feasible region. So find the overlapping section, and that's going to be our feasible region. You're going to list the ordered pairs of that feasible region, so the corner points, and then substitute each ordered pair into the objective function to find the value of the function at that point, and then choose the proper point to either maximize or so find either the maximum point or the minimum point of the objective function, depending on what the problem asks for. All right, so let's look at a real simple one here. So here, I guess when we're going to go back and do that. So here I've got corner points. I'm just giving them to you. Here's my objective function. So what I'm going to do is I'm going to plug those in. So put a 0 in for x and y. So I'm going to have that p is equal to 8 times 0. That's 0. 10 times 0 is 0. And so that is going to be 0. Then for 15, 0, my p is going to be equal to 8 times 15 plus 10 times 0. So that's going to be 120. And for 0, 13, we rounded that off, didn't we? We've got 8 times 0 plus 10 times 13, and that gives us 130. So right as of right now, it's the maximum. And then when I put in 5, 10, I get 8 times 5 plus 10 times 10. So that's 40 plus 100 is 140. So the maximum number of pounds we came up with is 140. So the answer is 140 pounds when we buy, and it was 5 pounds of Roma and 10 pounds of cherry tomatoes. And that's how you would write the answer on that. So that goes from that last one. So example 1, we're giving our constraints. So you can see we have our inequalities here, which we need to first graph. We're also given our objective function as well. So to graph the first one, if x is 0, y is going to be 1, 2, 3, 4, 5. And if y was 0, x is also going to be 1, 2, 3, 4, 5. So we're going to draw this here. It's less than 0, 0 is less than 5. So I will shade, I'm just going to kind of draw little arrows. I'm going to shade this way on that one. All right, then for the next one, I have that if x was 0, y is 8, so 6, 7, 8. And if y were 0, x is going to be 2, which is here. So I'm going to draw this as best I can. And I get that. And again, it's less than. So if I try the point 0, 0, 0, 0 is less than 8, which is true. So again, I'm going to shade this direction on that line. So you can see right now it's this little section, this little area right here. Then we have that x is, actually we have more than that. We have allotted to the side. But we also have that x is greater than 0. So that means that all my x's need to be on this side. And then y is greater than or equal to 0. So that means everything this way. So it just puts all of our answers in the first quadrant. So overlapping all those inequalities, we get this. So that would be our feasible region. So once we find our feasible region, we need to list the corner points of it. So again, we have 0, 0. Then when I do this one right here, that's 0, 5. Here, it appears to be 1. Oops, we can't do that. We're going to do a little bit of an intersection. I may have done a bad graph. We'll see. And then I've got this one right here, which is 2, 0. So what I'm going to do now is I'm going to do an additional elimination with this and figure out what this ordered pair is right there. So I chose to do the additional elimination method and came up with the x is 1 and y is 4. So even though it doesn't appear that way, if I was more careful, I think that line kind of curved a little bit when I drew it. I'm going to get that they intersected 1, 4 right there. Right, once we find our corner points, we're going to plug them into the objective function. So plugging in zeros, I get that g is equal to 0 plus 0, which is 0. If I put 0, 5 in, I get 0 plus 3 times 5 is 15. So I get 15. If I put 2, 0 in, I get 2 plus 0, which is 2. And if I put 1, 4 in, I get 1 plus 3 times 4 is 12, which is 13. So we see that our maximum, if we're trying to maximize it, this is our max. I'll put the words max right here. And the smallest value that we come up with is here, and that would be our minimum. So when they ask the question, what point maximizes the function, we would put the answer 0, 5 gives us the maximum answer. And what is the maximum of the function? 15 is the maximum of the function. All right, so stop the video. Well, hopefully you didn't stop. Why don't you go ahead and do the example 2 as a try me. So try this one right there. And then we'll stop.